Good morning, everybody. This is Math 0310. It's March the 1st. I can't believe it's already March. February is in the books. Some announcements about the class. First of all, some WebAssign homework. You've got the homework on section 9.1, 9.2, and 9.3. Remember, that's just one homework assignment. That's due March the 6th. And section 9.4's homework is also due March the 6th. Note that those are have been extended 2 days. The original due dates were March the 4th. I gave you a couple more days on those. And then you'll have 3 sections due 9.5, 9.6, 9.7 right at the end of spring break on March the 18th. So we were just talking about this before I went to the recording, but you do have some work that's due at the end of spring break. So you really want to get started on that and not get behind. Definitely. And I'll be sending reminders out over spring break, definitely. And then I've been mentioning this, but I will not have regular office hours over spring break at all, but I will be available for appointments over spring break. So if you want to get together with me in the WebEx room for some questions to be answered on your algebra homework, then there'll be times that you can meet with me over spring break, definitely. And I'll be checking email and Remind and WebAssign and all that. The Exam 2 review, I've been working on that over the last day or two, and it's pretty much finished. It's pretty close to being finished. It's not 100% finished, but pretty close. And for sure, by the middle of next week, I'll have that posted. I said posted by March the 8th, but I probably will have it posted before then, would be my guess. The Exam 2 window, remember, is March 22nd through the 27th. So that's the week after spring break. And I will be on campus. I haven't been talking about that much, but I will be on campus March the 21st and 22nd. March the 21st from 4 to 6 p.m. and March the 22nd from 9 to 11 a.m. So be thinking about that if you have if you want to meet with me in person and go over some algebra, that would be a great time. I know that Taylor and Raina both met with me before the last test, and I think they found that to be helpful. Hopefully they did. Found that to be helpful. And so I encourage all of you to think about coming by and seeing me in person for homework questions. All right, so today we will be covering sections 9.7 and 9.8 on higher order roots and fractions as exponents. Last time we talked about solving equations that had square roots. So we've done all of this stuff with square roots in chapter 9, and so today we're going to go on to cube roots and fourth roots and fifth roots and so on, and then also talk about exponents. Now I do want to kind of remind you that next week on Tuesday, we will go outside of the current textbook we're using, and we're going to go to the intermediate textbook for one section. And that one section I have lifted out of that book and have already posted that section on your Google site where it's syllabi and other documents. So you can just go to syllabi and other documents, because we're going to cover section 8.8 out of the intermediate algebra book, out of the intermediate algebra text. And I have put that section, the section is in syllabi and other documents on my Google site. And so you'll be able to go and refer to that section. There'll be homework problems there, things like that. And you do have WebAssign homework on that also. That's just the same. So the WebAssign homework won't look any different to you, but I did want to point out where the textbook sections are. All right, so today we are looking at what we call higher order roots. Now, a higher order root, this is what we're talking about. If we talk about the square root of x, right? We know that that's how we read this symbol, square root of x. And actually, technically, when we write that, that's actually an abbreviation for that notation, where there's actually a 2 written in the radical symbol. And that 2 is called the index of the root. That number right there. And when you're talking about a square root, the index is usually just not written down. So when we see a radical written without an index, you're talking about when we see a radical without the index, we're talking about a square root. And by the way, just referring back, Sandro just pointed out to me, maybe I have not uploaded the section yet on syllabi and other documents, but it will be there. I thought I had already uploaded it, and I must be thinking about my calculus class because they have a similar kind of section like that. So I'll upload that after class. So thank you for pointing that out to me, Sandra, and I'll definitely do that this afternoon because I've got the section pulled out. It's ready to go. I thought I had already posted it there. All right, so square roots we know are, how is this defined? The square root of x is equal to a, where a squared is equal to x, right? You're looking for a number that when you square it, you get x. And you also have to have that a, it's got to be positive or 0, right? And so when we write this symbol down, right, with a 3 right there, the index being a 3, now this is read the cube root of x. And this is what we're referring to when we talk about a higher order root, right? In this case, the index is 3. And so you're talking about the cube root of x is equal to a, where a cubed is equal to x. Right? You're looking for a number that is cubed that gives you x. So, as examples here, so let's write down some examples. So if we are talking about the cube root of 8, right, we're talking about the number that when you cube it, you get 8. Right? And so that the cube root of 8 is equal to 2 because 2 cubed is equal to 8. Notice right away a big difference between square roots and cube roots is that if we talk about the cube root of -8, well, remember with square roots, when we saw a negative underneath the square root, we talked about the fact that it was not a real number, right? That this x value had to be positive at the top, and so the square root of a negative number, you got to be, we just wrote not real. So the square root of -4, for example, up here is not a real number. Because there is no real number you can square to get -4. But -8 in a cube root is not the same thing here because there is a number, -2, that you can cube to get -8. So we don't have that restriction for cube roots, right? Because -2 cubed, -2 quantity cubed is equal to -8. Right, so the cube root of a positive number is a positive, and the cube root of a negative number is a negative, as it turns out. So the cube root of 27 would be equal to 3. And the cube root of -27 would be equal to -3. Right, when you cube 3, you get 27. And when you cube -3, you get -27. Cube root of 64 is 4, and the cube root of -64 is -4. Again, 4 cubed is equal to 64. Right, now you should know, as far as cubes and perfect cubes, you should definitely be able to recognize 8, 27, and 64, that those are all perfect cubes. Whoops, I'll come back to that section in a minute. But, you should be able to do further than that. So the cube root of 125, you should recognize as 5, because 5 cubed is equal to 125. And so the cube root of -125 is equal to -5. You should definitely know the cube root of 125. That 5 cubed is 125. 6 cubed is 216. You should recognize that one. The cube root of 216 is 6, and the cube root of negative 216 is negative 6, right? Because 6 cubed is equal to 216. All right, and so I would say at least up through 6 you should know, just by recognizing those on site. Now, if you're talking about variables, remember what the rule was for square roots. If you have powers of variables, so let's write powers of variables here. Remember that with square roots, we talked about this nice little shortcut here, that all you had to do is take the power and divide it by 2, that the square root of x squared, again, as long as x is positive, is going to be equal to x. And the square root of x to the 4th is equal to x squared, right? To find square roots, all you had to do is take the power and divide it by 2, right? The cube root of, or I'm sorry, the square root of x to the 6th is x cubed. Don't forget why that's true. Remember, this is true because, for example, x cubed, when you square it, you get x to the 6th because you multiply the exponents there. So it makes sense if you go backwards and you have to multiply, then to go the original direction, you have to divide, right? So each of these powers, when you have the square root of x to a power, then you just divide the exponent by 2. So the square root of x to the 20th would be x to the 10th. So with cube roots, so let's look at the cube root of x cubed right here, right? We are looking for a number that when you cube it, you get x cubed. And so that would be x, right? The cube root of x cubed is equal to x. And the cube root of x to the 6th would be x squared. You're looking for a number that when you cube it gives you x to the 6th, and that would be x squared. Again, the idea is you're multiplying the exponents. So in this case, you're always multiplying by 3 to check these. So it makes sense that when you go backwards that you are dividing. Right? The cube root of x to the 9th would be x cubed. And what number do you cube to get x to the 9th? That would be x to the 3rd power because you're multiplying the exponents. So what's the shortcut here? The shortcut is that you're taking these powers and you are simply dividing them by 3 now. Right? Notice you just divide by the index. So that's actually kind of easy to remember, that the cube root of x to the 24th would be x to the 8th. And the cube root of x to the 33rd would be x to the 11th, right? You just divide the exponent by 3, and you get the root that you're talking about for cube roots, right? So square roots you divide by 2, cube roots you divide by 3, right? So divide each exponent by 2 when you're talking about square roots, and with cube roots you divide each exponent by 3. And this is when you're talking about cube roots of powers of x, powers of a variable. We'll talk about other roots later, but you can already see what the pattern is going to be here. In fact, we could go ahead and deal with all the rest of these right now. That then if you had the 4th root of x to the 20th power, now what would you do? You would just divide the exponent by 4. And so this is going to be x to the 5th. And the 6th root of x to the 42nd would be x to the 7th. In this case, in both cases, x has to be positive, remember. With even roots, x has to be positive. Now you're at the 6th root of x to the 42, you're just dividing the power by the root, which is 6. The 9th root of x to the 27th would be x to the 3rd. You take the power 27 and divide it by the root. You get to x to the 3rd. right? So this pattern extends to all powers and all roots that you're talking about. I'll talk about simplifying some in a few minutes. All right, so let's see. Let's go back to constants here. So we're talking about cube roots, so let's talk about fourth roots now. So the fourth root of 16, for example. So let's get away from powers of a variable for a while. So what are you doing here? You're looking for a number that when you raise it to the fourth power gives you 16. And so the fourth root of 16 would be equal to 2, because 2 to the fourth power is equal to 16. And remember, this is defined to be the positive number that raised to the fourth power equals 16. So the fourth root has to be a positive number, right? It can't be a negative number. Just like square roots, it's got to be equal to a positive number. All right, fourth roots, I don't expect you to know that many of these by sight. So you have the fourth root of 16 is equal to 2. The fourth root of 81 would be equal to 3, right? Because 3 to the fourth power is equal to 81. I don't expect you to recognize perfect fourth roots, very many of these by sight, to be honest with you. The fourth root of 625 is 5, because 5 to the fourth power is equal to 625. Like I said, I don't expect you to recognize very many of those on sight. The fifth root of 32. You're looking for a number that when you raise it to the fifth power, you get 32. And so that would be 2. Right? The fifth root of 32 is equal to 2. And the fifth root of negative 32 is equal to negative 2, because negative 2 to the fifth power is equal to negative 32. Notice with fourth roots, right? Fourth roots, if you have a negative number here, you write that it's not real. Right? So in fact, let's go ahead and write that out right here, right now. So with even roots, right, whatever the root is, let's say that the root is n, so then you're talking about the nth root of a negative number is not real. Odd roots, right, so n is odd in this case, then the nth root of a negative number is a negative number. Right, so let's kind of look back at that again. So kind of write it out underneath here. So the square root of 9 we know is 3. The square root of negative 9 we know is not real. The cube root of, let's say, 27 is 3. The cube root of negative 27 is negative 3, right? Cube root, that's fine. You get a real number, you just get a negative answer. The fourth root of 16 is 2. The fourth root of negative 16 is not real. The fifth root of 32 is 2. And the fifth root of negative 32 is negative 2. So you can see how even roots you get of a negative number are not real. Odd roots of negative numbers are negative numbers. All right. So now let's look a little bit at simplifying higher order roots. Simplifying higher order roots. And this is what I'm talking about when I talk about simplifying. So recall, with a square root, if you had this square root of 12, for example, 12 is not a perfect square. So there is no root there that you can write as an integer or as a whole number. But you can simplify the square root of 12. And remember, the way we talked about doing that is you break it up as a multiplication problem. And one of the factors had to be a perfect square. Right, so in this case, we don't break square root of 12 up as 6 and 2 because neither 2 or 6 is a perfect square. Instead, we use 4 and 3. and then write the square root of 4 is 2, and you get 2 times the square root of 3, right? And you've simplified the square root of 12. The square root of, let's say, 90, we would break that up as the square root of 9 times the square root of 10, right? And so that would give me 3 times the square root of 10, right? And again, why? Because why would you use 9 and 10? Is because 9 is a perfect square. Right? You needed a factor that is a perfect square when you break it up as a multiplication problem. All right, and then you can simplify it. So that's why in 12 we don't use 2 times 6, and with 90 we don't use, for example, 5 times 18 as an example. All right, 5 times 18 is 90, but neither 5 or 18 is a perfect square. So you wouldn't want to use that factorization. All right, so with cube roots, we're doing exactly the same thing. So let's look at simplifying cube roots. And by the way, we'll look at simplifying cube roots. We'll look a little tiny bit at simplifying fourth roots, but very little. And then fifth roots, sixth roots, we're just not going to talk about simplifying higher order roots. We'll concentrate on cube roots for the most part. All right, so let's say we have the cube root of 16. Now 16 is not a perfect cube. So what we want to do is we want to break this up, this cube root of 16 up into 2 factors, 2 cube root factors, but we want one of those to have a perfect, not a perfect square, but a perfect cube inside. Right? And so you've got to think about the perfect cubes, and you have to have this list kind of, and what I would do if I were you, I'd actually write this list down. So you have it sitting in front of you, that the perfect cubes are 1, 8, 27, 64, 125, 216, right? Those are the factors that you're trying to use to simplify. So with the cube root of 16, you could break that up as 8 and 2, right? Because the cube root of 8 is a perfect cube. And so what do you get here? You get 2 times the cube root of 2. Right, and you've simplified the cube root of 16. Okay, the cube root of, let's say, 54. Cube root of 54, you could break up that into 2 factors, right? One of them being 27, right? You wouldn't use 9 and 6 because 9 and 6 are not perfect cubes. Neither of 9 or 6 is a perfect cube. You are looking for a factor with that is a perfect cube. And so the cube root of 27, 27 is a perfect cube. That's the one you want to use. And so this would be 3 times the cube root of 2. Right? You're trying to find a number in that list, this list of perfect cubes over here, that is a factor of the number that you're looking at. Cube root of 375. Now, it looks like it might be hard, but that's really not too bad. The factor there that's the perfect cube that's a factor of the cube root of 375 is 125. This breaks up as the cube root of 125 times the cube root of 3. Right? The 125 is my perfect cube in this case. And so this would give me 5 times the cube root of 3. All right, so I kind of wanted to point out how you would simplify cube roots. Now let's look at cube roots that have powers of x. So we saw on 2 screens ago that what are you going to do to evaluate cube roots of a power of x is you divide each exponent by 3, right? All right, so in our problem then, if you're going to take the cube root of x to the 15th, that's not a big deal because 15 is divisible by 3. This is x to the 5th. It's easy to write that out. But what if you had something like this, the cube root of x to the 8th power? Cube root of x to the 8th. See, 8 is not divisible by 3, right? So 8 is not divisible by 3. And so we need to simplify in this case. We're not evaluating, we need to simplify. So what we need to do is break this up into 2 cube roots, 2 powers of x here, and one of them needs to have a power that's divisible by 3. And you need to have the biggest one, right? So we need a power divisible by 3. So can you tell me what's the biggest power that's less than 8 that's divisible by 3? So those of you who are with me live right now, what's the power that's less than 8 that's divisible by 3? The biggest one.
3.
Now 3 is divisible by 3, but can I do better than that? Trisha? Anybody? Anybody have a power that's divisible by 3 that's less than 8 besides just 3? Okay, Trisha sent me a text message and she said 6, which is exactly right. Good work, right? If I use x to the 6, 6 is divisible by 3, right? That's the one I want. Now, how many x's are left? Remember, I started with 8 x's, right? For all of you, so right, I had x to the 8th power. So I'm going to use 6 of them in this first radical. So how many are left for the second radical? I'm hoping to hear somebody say 2. There you go, 2. That's right. And so x to the 6th times x to the 2nd is x to the 8th. And 6 is the biggest one you can use there. And so then the cube root of x to the 6th, you take the power and you divide it by the root. So you get x squared. And then the cube root of x squared just comes down for the ride, like that. And this is the simplified version of the cube root of x to the 8th. Now I know it's not really a simpler form at all, but we consider this the simplified version because the number underneath the radical is as small as we can make it. All right, so let's do another one like that. The cube root of x to the 20th power. So 20 is not divisible by 3. So I can't evaluate this. So instead I simplify it, break it up into 2 cube roots, 2 powers of x. So what would be the biggest power of x less than 20 that's divisible by 3? Good, Sandra. Sandra texted me 18. That's exactly right. So I have x to the 18th right here. That's the biggest power less than 20 that's divisible by 3. How many x's does that leave me with for the second radical? 2 of them. Right, x to the 18th times x squared is x to the 20th. And then go ahead and evaluate the cube root of x to the 18th. You divide 18 by 3, which is 6. So this is x to the 6th times the cube root of x squared. Like that. All right, let's look at a couple of problems that are kind of combinations of those things. So let's say we have the cube root of 64x to the 12th. Cube root of 64x to the 12th. Now see, look, this is one that you're going to evaluate. You're not going to simplify here, you're going to evaluate. Because both of these things are perfect cubes. You know the cube root of 64 is 4, right? Because 4 cubed is 64. And x to the 12th, that power is divisible by 3. So I can go ahead and evaluate that and get x to the 4th power, right? And so this is actually a radical that we evaluate. We get 4x to the 4th, right? We know that 4 cubed is 64, and we know that x to the 4th cubed is x to the 12th. Right, so this is actually one that we evaluate. This one, however, is one that we're going to have to simplify. You have the cube root of 24 x to the 4th. cube root of x, 24x to the fourth. So you see how 24 is not a perfect cube, so I can't evaluate that. And x to the 4 is not divisible by 3, so I can't evaluate that one. So instead what I do is I simplify. Right, so I break this up as 2 cube roots. All right, so 24, how would we break up 24 is 2 factors. And remember, one of the factors has to be a perfect cube. Anybody have an idea how I break it up? These would be perfect cubes right here. So what's a factor of 24? And don't forget what the perfect cubes are. Right, we wrote that list down before. Right, so what's a factor of 24 that's a perfect cube? Gianna, that's right, is 8. Sandra also said 8. And so we're going to break this up as 8 and 3. Right, because 8's a perfect cube. X to the 4th, the 4 is not divisible by 3. And so instead what we do is we break it up to simplify it. And we need a power less than 4 that's divisible by 3. This would be x to the 3rd. And so that would leave me with 1x left for the other radical. Right, so the perfect cubes go into this radical, and then this is kind of like the leftovers right here. Right, and so then we evaluate. The cube root of 8x cubed is 2x, and then this would be times the cube root of 3x. By the way, don't forget to continue to write the index down each step. You know, this is a cube root problem, so notice all these radicals are cube roots. I can't tell you how many times I'll see a problem like this, and the student will tell me that the answer is 2x times the square root of 3x. Right, and that student has just forgotten to write the index down. That's a totally different expression. And so please don't play magician and make the index disappear, or don't change the index. Right? If you start off with a cube root problem, you're going to finish with a cube root problem in a situation like this. All right, let's look at another example like that. Let's say we have the cube root, let's say of 40, x to the 5th, y cubed, z to the 10th. All right, so this is absolutely as messy as you'd see for a cube root. You probably on a test you wouldn't even see anything quite this messy. So let's look at each factor here. The 40 is not a perfect cube root. So we know we're going to break up this radical into 2 radical factors. So how would I split up the 40? What factor of 40 is a perfect cube? And that would be, 8. Not 8 and 5. That's right. Right. So we're going to write 8 and 5. Sandra, you write 8 and 20. I'm not really sure what you meant by 8 and 20, but because you're just looking for 2 numbers to multiply to give 40, right? And so that would be 8 and 5. So you got the 8 part right. All right, so then the x to the 5th, right? 5 is not divisible by 3, and so I break it x to the 5th up into 2 factors where one of the powers is divisible by 3. And so that would be x cubed and x squared, right? 3 is divisible by 3, and then I have 2 left over. Now the next one is y cubed, but notice the y cubed is divisible by 3. That one doesn't need to be simplified. That one just can be evaluated. So I just put the y to the 3rd over here in that first radical. And then the z to the 10th, again, you have a power not divisible by 3. So I need to break this up as z and a z. And what powers do I use here? The biggest power less than 10 that's divisible by 3 is 9. And so I put a 9 there, and then that would leave me a z to the 1st in the second expression. And see, so notice that in this first radical, these factors are all perfect cubes. I can evaluate every one of those. Right? And then in the second one, these are all just the leftovers after you found those first factors. All right, and so then cube root of 8 is 2. The cube root of x cubed, you divide the power by the root, and so this would be x to the first. Y to the third, do the same thing. That's y to the first. And then z to the ninth. 9 divided by 3 is 3, so this is z to the third. And then this would be multiplied by the cube root of 5x squared z, like that. And so you've simplified it. And like I said, that's about certainly as messy as you're going to see on a problem like that. You're not going to have to worry about that beyond that. All right. So let's see. Let's look at 1/4 root as far as, so recall that with a fourth root, if you have a power, what do? You divide. Again, just like all of these, you divide the power by the root. And so this would be x to the 5th power. You can evaluate that one. So if the power is not divisible by 4, like x to the 9th, for example, then you break it up as 2 factors, 2 powers of x, where one of them is divisible by 4. And so the biggest power less than 9 that's divisible by 4 is 8. So this would be x to the 8th and x to the 1st. And then the fourth root of x to the 8th, you divide the power by the root, you get x squared. And then this would be times the fourth root of x. Now, I'm not going to go any further with simplifying fourth roots. That certainly is about as far as you'd have to deal with that with fourth roots. I'm not going to go crazy with that at all. Let's do one more example of a fourth root, and then that will be it for fourth root. So let's say we have the fourth root of 48, and let's say x to the 7th power. So 48 is not a perfect fourth root, but 16 is. And so 48, I'd break up as 16 and 3, because I know the fourth root of 16 is 2. And then x to the 7th is not divisible by 4. So I use the biggest power less than x to the 7th that is divisible by 4, and that would be x to the 4th. And so since I used 4 x's in the first radical, I started with 7. So I have 3 x's in the second radical. All right, x to the 4th times x cubed is x to the 7th. And then simply evaluate the fourth root of 16 is 2. The fourth root of x to the 4th, 4 divided by 4 is 1, so that's x to the 1st. And then this would be times the fourth root of 3x cubed. And you've simplified it. All right, so we have kind of now gone through higher order roots and doing some evaluating with higher order roots here. I am generally not going to be, well, one situation where I want to rationalize, we're not going to rationalize anything except rationalizing simple cube roots. All right, so let's say I have 1 over the cube root of 2. Now remember, rationalizing means taking the fraction and rewriting it so you don't have a radical in the denominator. And so what you do is you're multiplying the top and bottom by the same thing and trying to eliminate the radical that way. Now, with square roots, if you recall with square roots, if you had 1 over the square root of 2, all you had to do there is just multiply top and bottom by the square root of 2. Because square root of 2 times the square root of 2, that's the square root of Bob times the square root of Bob, right? That gives you Bob. And so that's just 2. And then you get the square root of 2 in the numerator. Now that does not work with cube roots, unfortunately. It doesn't work just to multiply the expression by itself like that, because these are not squares, these are cubes that we're worried about here. And so, again, what I would do here is I would just take my little list of perfect cubes And I would take the number that I've got, so in this case it's 2, and start dividing it to each one of those until you hit a perfect cube that 2 actually divides into. So 2 divides into 8. How many times does 2 divide into 8? 8 divided by 2 is 4. And so that's what you do, is you multiply on this one the top and the bottom by the cube root of 4. That's what's going to rationalize this denominator, is multiplying top and bottom by the cube root of 4. Watch what happens. So in the numerator, you just get the cube root of 4. That's not a big deal. But in the denominator, you have the cube root of 2 times the cube root of 4 is the cube root of 8. You multiply the two radicals together. Seeing what happens, you end up with a perfect cube underneath the radical in the denominator. So the denominator is just a 2. And so you have the cube root of 4 over 2. Right? And so you've rationalized it. All right, if you have 5 over the cube root of 9. So here's an example right here. Here's an example right here. So what do? You take the 9 and you start going through your little list, for the perfect cubes. 1 divided by 9, 8 divided by 9, 27 divided by 9, and so on. And you stop, right? 27 is divisible by 9. Right? 27 divided by 9 is 3. And so on this one, I'm going to multiply top and bottom by the cube root of 3 over the cube root of 3. And so that would give you, in the numerator, 5 times the cube root of 3. I can't multiply those, so I just leave that alone. The denominator, this is the cube root of 27. Right? 9 times 3 is 27. But you know the cube root of 27 is 3. So you have 5 times the cube root of 3 over 3. And you've rationalized it. Now that's absolutely as difficult as I would ever look at with rationalizing cube roots. So beyond that, don't worry about cube roots and rationalizing. And we will do no rationalizing with 4th roots or 5th roots or 6th roots, anything like that. A little tiny bit with cube roots. Do not worry too much about that, okay? All right, so that's our discussion kind of higher order roots. But actually, we're going to continue that in the next section. Because what we want to do in the next section, in this last section of the chapter, is look at exponents. And in particular, we want to look at fractions as exponents. And what we're going to see, actually, is this is actually just a repeat of what we just did. It's just written out differently. But that fractions as exponents really are connected to these higher order roots in a big way. All right, so we know that if you take 5 and you square it, you get 25, right? And so what do we know then? That 5 represents the square root of 25. Right? Square root of 25 is equal to 5 right there. Right? So that 5 represented the square root of the 25. So when you take a number and you square it, right, what happens? You get that. And actually, let me write this out differently. Let me erase that real quick. Let me do it this way. We have the square root of 3. That's what I wanted to start with, actually. And I square it. What do we know? We know that the square root of Bob squared, we talked a lot about that in the last lecture, is Bob. So the square root of 3 squared is 3. Right? So now, let's take 3 to the 1/2 power. That's what we want to talk about here, and raise that to the 2nd power. Now what happens there? The rule of exponents, remember there, is that you multiply those exponents. Right? You multiply exponents here. And so you have 2 times 1/2, but 2 times 1/2 is 2 halves, or 1. So you just get 3 there also. So notice what I want you to see is that when you take the square root of 3 and you square it, you get 3. when you take 3 to the 1/2 power and square it, you get 3 there also. You get the same thing. So the only conclusion here is, if I could spell the word conclusion, that would be good. The only conclusion is that square root of 3 and 3 to the 1/2 power mean the same thing. So when you take a number and raise it to the 1/2 power, you're really talking about the square root. So when you take 25 and raise it to the 1/2 power, you're talking about the square root of 25, that these mean the same thing, and that would be equal to 5. And 49 to the 1/2 power really means the same thing as the square root of 49, and that gives you 7. Right? And so then if you think about, go like one step further here, if you have 16 to the 3/2 power, not 1/2 power, but 3/2 power, well, you could rewrite that using rules of exponents as 16 to the 1/2 to the 3. And then what does the 16 to the 1/2 power really mean? That really means the square root of 16, right, to the 3rd power, like that. And so what are you doing? You're talking about taking the square root of 16, and then you are raising it to the 3rd power. So this is 4 to the 3rd power, or 64. Now, if you kind of go through that whole process, what you were doing is when you took the 16 and raised it to the 3/2 power, that 2 represented the root that you were talking about, that you're talking about the square root right there. And then the 3 is the power that you raised the number to after you took the square root. And so this was represented the square root of 16 raised to the 3rd power. Right, so let's not do a number that big. Let's say 4 to the 5/2 power. Then what are you doing? You're talking about taking the square root, that denominator represents the root, raised to the 5th power. So in words, this is the square root of 4 raised to the 5th power. Right, and so what is the square root of 4? Well, that's 2 to the 5th power, or 32. So 4 to the 5/2 power is equal to 32. In general, what this is going to, in general, always be true here. We have that if you have x to the a over b power, that the b represents the root that you're talking about, and the a represents the power. And just like we've seen before, if you have an even root of a negative number, you get that's still not a real number, right? Just like we've seen before, nothing else has changed. And another way to write the same rule is to write this as that x to the a over b power is the b root of x raised to the a power, like that. Or you could write that as the b root of x raised to the a, like that. It means the same thing. All right, so 27 to the 2/3 power. All right, think about what each of those numbers means then. The 3 in the bottom represents the root you were talking about. This is a cube root problem. And then the 2 represents the power you were talking about. This is the square root. I'm sorry, the square. Not the square root, the square. 2nd power. So 27, the cube root of 27 is 3 to the 2nd power, and that would be equal to 9. All right, you'll get used to evaluating these. 125 to the negative 2/3 power. Now, don't freak out with the negative exponents. The rules are the same as what we've seen before with all of these exponents. And so, first of all, remember that a negative exponent takes the factor and moves it to the other part of the fraction. So it takes a number like this and actually turns it into a fraction. Don't forget that that's the rule for negative exponents. And so you have 1 over 125 to the positive 2/3, right? The negative exponent brings the factor to the denominator. Don't forget that x to the negative a is 1 over x to the a. And then you just evaluate it from here. So the 125 to the 2/3 power, the denominator is the root, the numerator is the exponent, or the power. And so this is the cube root of 125 to the second power. So the cube root of 125 would be 5, and that'd be raised to the second power. This is 1 over 25. All right, the next example, negative 100 to the 5/2 power. Just be really careful here. This root is 2. It's the square root. That's an even root right there. And this is an even root of a negative number. So I don't even care about the 5 anymore. This is an even root of a negative number. I just write that this is not real at this point. Right? An odd root of a negative number, remember, is okay. Even root of a negative number is a problem. So if we have negative 27 raised to the 5/3 power, in this case, the root is odd. So this one is okay. And the numerator is a power. So this is the cube root of negative 27. That's negative 3 raised to the 5th power. And then that's a negative answer. And negative 3 to the 5th power would end up being negative 243. Right, it's 3 times 3 times 3 times 3 times 3. Right, and so you get negative 243. Now the answer doesn't have to be negative at the end when you have a root like this. So negative 8 to the 4/3 power, right? The denominator is the root. The numerator is the power. So this is the cube root of negative 8, which is negative 2. But this is raised to the 4th power, and this is an even power now. And so negative 3 to the 4th power is positive 16. Right? So it depends on how the power works as to whether your answer ends up being positive or negative at the end. But definitely, I want you to always keep this in mind, that when you have a fraction as an exponent, that the denominator represents the root, and the numerator represents the power that you were talking about in the problem. Now what I've done, I want to flip back a few screens here, is we're going to look at some more problems here to finish class out. But what I've pasted in here is a document that I've made that I use for my intermediate algebra classes that it's a summary of all the rules of exponents that we have discussed. Right, gone way back towards the beginning of the semester when we did rules of exponents, right? And you've got x to the a times x to the b is equal to x to the a plus b, right? So this is what happens when you multiply like bases, you add exponents. Notice that after I state the rule, then I try to state it in words afterwards. Right, and then after I've stated the rule and then stated it in words, then I've got examples of that rule written afterwards, right, where in this case you're multiplying like bases together like this. Right, so as you go through this, you've got these 8 rules. So these first rules are all rules that we talked about at the beginning of the semester and you would have talked about in a Math 0308 class. Right? And so I wanted to go back and kind of summarize all these rules. I think this is a good summary sheet for you to have. If I were you, I'd go to these notes. So this is going to be in the notes for this lecture. But what I would do is I would go through and print this, right? So you have these rules sitting in front of you so that you can refer to it when you need this. As far as, now you can't bring it to an exam, but you can use it for study purposes, definitely. And these are rules that a college algebra student really needs to know how to deal with all of these different situations. Here's the rule 7 is the rule for negative exponents. Rule 8 is the rule that we have just started talking about, where you've got x to the a over b power, and notice it's power divided by root, right? And so what I've tried to do here is, in most cases, tried to write out what the rule says actually in words, if it was appropriate. So please kind of keep this sheet in mind. When you're doing exponent problems, right? I think this is a good sheet to have and to refer to. All right, so let's look at some more examples. And what I'm doing, I think I could have done this more efficiently here to get to this last page. Let's look at some problems. So these are out of section 9.8 in your book. And we're talking about simplifying different types of expressions. All right, so this is on page 1125 of your book. Let's see. So this is page 1125. And so we want to work through some of these problems. So this is problem number 560b. 560b is 9 to the negative 3 halves. Okay, so this is the kind of problem we've just talked about. So you get rid of the negative exponent, right, by rewriting this as a fraction. You bring the factor to the denominator, so the 9 goes to the denominator, and the exponent now becomes positive. And then what do we do here? We recall that the denominator represents the root, and the numerator and that exponent represents the power. And so this is the square root of 9 raised to the third power. So the square root of 9 is 3, and this would be raised to the third power, and so you get 1 over 27. All right, now the next problem, this is 562b. So 562b is almost the same thing, and this is a problem that frequently causes students trouble. It's the negative of 9 to the negative 3 halves power. Now, the base on this is, you got to be careful. Don't confuse, let's say, don't confuse with this problem. And that would be the negative 9 to the negative 3 halves power. Right? The base on the first one, the number you're raising to a power is positive 9. The base on the second one is negative 9. There's a big difference in those two problems. There's no parentheses in that first one. So in this first one, that negative sign just trails along and comes along for the ride, and you just deal with the problem 9 to the negative 3 halves. So you get rid of the negative exponent, just like we did before, then raise 9 to the 3 halves power, just like we did, and you get 27. So this is negative 1 over 27. This negative sign had 0 to do with the problem. It just trailed along from step to step. Right? It didn't have anything to do with it. But on the second problem, the base is a negative 9, and so this is 1 over negative 9 to the positive 3 halves. And then we have root and power here. And so this is the square root of negative 9, and I stop right there, and I write not real. right? Because it's an even root of a negative number. Really, really, really easy to make a mistake on a problem like that, so you really have to watch that. All right, problem 566A. 566A. You have 4 to the 5/8 times 4 to the 11/8. Right, so this is a problem where you would refer back to the rules of exponents. The bases are the same here. So remember, the rule here is to add the exponents. It doesn't matter if the exponents are fractions. The rules of exponents are all still the same. Those haven't changed. So this is 4 to the 5/8 plus 11/8. Right, notice I just added the exponents. And so this would be 4 to the 16/8. All right, that's all you're doing. And then if there is a way to simplify that exponent, you do that. In 4 to the 16/8, that's 4 to the second. And so you end up with 16. All right, so you need to know when to add, subtract, and multiply exponents. That's something that's you're going to be confronted with often, so you have to watch for that. So let's say you have, this is 568A. 568A is 5 to the 1/2 times 5 to the 7/2. So again, you're multiplying bases together, so you add exponents in this case. And so when I add exponents, this would be 5 to the 1/2 plus 7/2. You're going to have problems that are going to be this straightforward on the next exam. I want to know that you know when to add, subtract, and to multiply exponents. So this would be 5 to the 8/2, or 5 to the 4th power, or 625. Right, so that's a problem where you're going to go ahead and add the exponents. All right, what if you had, this is an example, what if you have x to the 3/4 times x to the 1/5? Well, that problem's exactly the same as the first three. No difference between that one and the first three, except for the fact, well, we do have to add the exponents because we're multiplying like bases together. The only problem with adding the exponents here is that the exponents don't have a common denominator. Right? So you have 3/4 plus 1/5. Please don't add those together. Right? You can't add fractions together that don't have the same denominator. So you need a common denominator here, which would be 20. So this is x to the 15/20, right? You multiply the first one by 5 over 5. Right? This is 5 over 5 right here. Second one by 4 over 4. And so this would be plus 4/20. And so then you add the exponents and you get 19/20. Nothing I can do with the 19/20, and so that would actually be my final answer right there. Right, so you need to be able to add exponents at the appropriate time. When you're multiplying like bases together, right, you're adding the exponents. All right, so let's move on. Let's talk about a problem like this. This is number 570A. 570A, we have m to the 6th raised to the 5/2 power. Now this one is not like the last problem where we had like bases multiplied together. This was a problem where we have something raised to a power and then raised to a power again. So the rule here is to multiply exponents, right? And that's a rule we talked about a long time ago this semester. That's what we're going to do here is multiply those exponents. Now that 6 is technically 6 over 1. So this is 6 over 1 times 5 over 2. And so that gives you 30 over 2. If that's the way you want to write it, that's fine. This is m to the 30 over 2. don't leave it like that. You go ahead and simplify that exponent. So this is m to the 15th. All right, let's see. Let's say we have problem number 572, 572b. 572b, we have y to the 20th, and that is raised to the 2/5 power. All right, so this is an example, once again, where we would multiply the exponents. Right, and so if you want to, you can do the multiplication off to the side like I did in the previous problem. So this is 20 over 1 times 2 over 5. So that's 40 over 5. This is y to the 40 over 5 power. And then you reduce that fraction, which does simplify, and you get y to the 8th. All right, this is an example. Let's say we have 64 x to the 3rd power, and this is raised to the 3/2 power. All right, so you first of all raise each factor to the 3/2 power, right? That's the rule. When you have factors raised to a power, you raise each factor individually to that power. Right, so we're raising each factor to the 3/2 power. And then that first fraction, what have you got? Or that first factor, you've got 64 to the 3/2. Remember, the denominator is the root, the numerator is the power. Right, and so this is the square root of 64 cubed. We'll do this off to the side here. So the square root of 64 is 8. This is 8 to the 3rd power. And then 8 to the 3rd power is actually 512. It's 8 times 8 times 8, 512. And then the x to the 3rd to the 3/2 power, you multiply the exponents here. And so that's 3 times 3/2, or 3 over 1 times 3/2, which is 9/2. So that's x to the 9/2 power. So our final answer here is 512 x to the 9/2 power. Notice I kind of did some scratch work and I did each little piece off to the side. That way I didn't have to worry about doing too much at any one given time in the problem. All right, we're moving along here. Number 574, C. We have r to the 4/5 over r to the 9/5. So remember the idea here, when you're dividing like bases, you subtract exponents. Now in this problem, what we've also decided to do, this has been a while since we've done this in class, is not only are you subtracting these exponents, but you put the r where the bigger exponent is. So the bigger exponent's in the denominator, so that's where the r is going to go here. And then it'll be just a 1 in the numerator, and so this would be 9/5 minus 4/5 right here in the denominator. And so this gives me 1 over r to the 5/5, which is 1, and so this is just 1 over r. All right, this example, if we had x to the 6/5 over x to the 4/3. Now, once again, in this problem, we are subtracting exponents. Subtract exponents here. Right? Because you're dividing like bases, so you subtract exponents in this problem. But what I would do first is I'd first go ahead and get a common denominator on those exponents to see where the bigger x is, where the bigger power is, rather. So the common denominator here is 15. Right, on the first one, we're going to multiply by 3 over 3. Second, we're going to multiply by 5 over 5. So you have x to the 18/15 in the numerator, and in the denominator you have x to the 20/15. And so notice the bigger exponent is actually in the denominator in this one. And so you have an x in the denominator and a 1 in the numerator. And then you subtract exponents, 20/15 minus 18/15. And so you have 1 over x to the 2/15. Right, in the denominator, the x to the 2/15 goes in the denominator. Okay, this is number 580b. 580b. You have 100 v to the 2/5, and that's all raised to the 3/2. All right, so we've seen here that when you have factors, you raise each factor separately to that power. I would take my time and not try to do too much in any given step here. So I'd write this as 103 to the 3/2 power times v to the 2/5 to the 3/2 power. Notice I raised each factor separately to the 3/2 power. And then I would probably just do each of these off to the side here. The 100 to the 3/2, the denominator is the root, the numerator is the power. How many times have I written that out today already? Right, so the square root of 100 is 10 to the 3rd power. Oh my gosh, 10 to the 3rd power. Students go nuts on 10 to the 3rd power and all sorts of crazy answers there. It's not 30. Please don't tell me it's 30. Right, this is 10 times 10 times 10. This is just 1,000. And just adding, the 3 tells you how many zeros there are. And then in the second factor, you have v to the 2/5 raised to the 3/2. So you're multiplying the exponents here. And so you multiply exponents, you get v to the 6/10 power. Right, just 2 times 3 and 5 times 2. Doesn't matter that you don't have a common denominator. That's okay. So this is 1,000 v to the 6/10 power. And somewhere along the line, you would take that 6/10. Don't leave it like that. And write it as 3/5. 1,000 v to the 3/5 power. Right, and that would be the simplified expression there. All right, we're getting close to finishing up here. We just have 1 or 2 more examples to work, and then we're going to be kind of finished with all this. So let's say we have, next problem, let's say we have x to the 4th, y to the 2/5 over x to the 3/2, y to the 7/8. All right, so this is a little bit messy here, but all you're doing is looking at the x's and the y's kind of separately, right? You've got 2 separate problems here. You have x to the 4th over x to the 3/2. Because this is all multiplication, we can think of it this way. And you've got y to the 2/5 over y to the 7/8. So if you want to, you could actually just do each of those problems kind of separately and then kind of combine your answers here. So what are you doing? You're definitely subtracting the exponents here. All right, so you subtract exponents, but you need a common denominator to do that. This is 4/1, so the common denominator here is 2. The x to the 3/2 is okay like it is. But in the first fraction, I multiply top and bottom by 2/2. And so this is x to the 8/2 power. And so then you can subtract exponents. The x goes in the numerator and a 1 in the denominator, and this is x to the 5/2 power. Right, so coming up to my answer up here, there's going to be an x to the 5/2 in the numerator. And then with the y's, you do the same thing. You have y to the 2/5 over y to the 7/8. So you need a common denominator there. on the exponents because you're going to subtract again. And so you'd multiply the first one by 8 over 8 and the second one by 5 over 5 to get a common denominator on those exponents. So you have y to the 16/40 over y to the 35/40. And so on this one, the y would go in the denominator because that's where the bigger exponent is. And then you have 35/40 minus 16/40 would be 19/40. And so you have a y to the 19/40 up here in the denominator, like that. Okay, so kind of wanted to go through some examples like that. And so you've got a lot of problems. I've worked a lot of examples in the notes. You definitely need to go back through and kind of work through some of the easier examples. Start with easier examples first and work your way through the harder examples. I would definitely take advantage of the problems out of the textbook. In this section, there's a ton of problems here in sections 9-7 and 9-8. And for practice, I would probably try to deal with the practice problems before I did WebAssign on this section, to be honest with you. So textbook practice, try to do some problems out of the textbook first before you go to WebAssign because there's more easier examples in the textbook than there is in WebAssign. So textbook practice on 9-7, there's, like I said, a ton of problems. So this would be 443. Now the author goes a little bit nuts with some of this, so I'm going to kind of limit it to up through like 479. The author goes a little bit nuts on some of that. And then again, 501 through 511. That's in section 9-7, and then 9-8. Lots and lots and lots of good problems on 9-8. This is on page 1123. Problems 525. Really through, I mean, the author has put just a tremendous number of problems in this exercise set. So lots of practice problems here. And really anything up through 597 would work here. So try to work at least some of this. When you're bored over spring break, go to these problems and see if you can work through some of them. The answers are, remember, on the back of the textbook. Okay, so I have office hours today from 11 to noon, and then not again until Sunday, 8:30 to 9:30. Please don't hesitate to contact me if you have questions. If you want to make an appointment to come by and see me outside of those hours in my WebEx office, don't hesitate to email me or send me a remind message, and we'll work out a time where I can meet with you. Does anybody have any questions that they want to ask about?
No question.
All right, so go home and practice, or stay at home if that's where you are, which a lot of you are at home. I know, Sandra, you're not, you're at work. But if you have questions, get some practice in. Don't hesitate to come by for help. I'll be happy to help you out. Otherwise, you guys have a great day. And